There is another family of transistors called the bipolar junction transistor or the BJT for short. The way the bipolar transistor operates is a lot more complicated than the way the MOS transistor operates. There is nothing to get intimidated about the bipolar transistor, it's just one more device. And like the MOS transistor, it's a 3-terminal device. In the MOS transistor, this is the drain, this is the source, this is the gate. This is an NMOS transistor. The bipolar transistor, this terminal is called the collector. This is called the base and this is called the emitter. And quiescent current flows again from the collector to the emitter. This device is called an NPN transistor. And this is very analogous to an NMOS transistor, where the gate controls the flow of current between the drain and the source. In the bipolar transistor, the base controls the flow of current between the collector and the emitter. So for short, the NPN transistor is often denoted by the collector, the base and the emitter. When we saw those characteristics for an ideal 2-port which would give you gain, we said there exists a device called the MOSFET which does this. The bipolar transistor is also a very similar device, and just that the nature of those equations are different, that's all. In fact, the equations for the bipolar transistor are a lot simpler than that in a MOS transistor. If I plot VCE on the x-axis and IC on the y-axis, this is exactly what we did for the MOS case also. Okay, we plotted VDS on the x-axis and ID on the y-axis. Just the terminal names have changed, so the letters here must change. The characteristics, not surprisingly, look very similar. And these curves got to be for different values of VBE. And where will you get gain? Which region of operation would you want to bias the transistor to get gain? This is the region where you will get gain. Unfortunately, this region is not called the saturation region for the bipolar case. This is called the active region, and this area where you do not want to operate the transistor is called the saturation region. The nomenclature has got to do with the way the device works, so you can't blame a circuit designer for this. So this is where you do not want to operate the device. So if a MOS transistor is operating in saturation, you like it. If the bipolar transistor is operating in saturation, you don't like it. And it turns out that unlike the MOS transistor where the edge of the triode region was a parabola like this, in the bipolar transistor, the edge of the saturation region is a constant voltage. So this makes life a lot easier because you don't have to worry about VGS, or rather if VGS minus VT is larger, the triode region occurs earlier as you reduce the voltage, but here this is a constant voltage. This is often referred to as VCE SAT, and that is the minimum voltage required for the between the collector and emitter, below which the transistor will no longer behave like an active device. So you want to maintain a minimum voltage of VCE SAT between the collector and emitter, okay, otherwise you are in trouble. Otherwise, what do you think you would expect to happen to an amplifier? Gain was decreasing, so sine wave will clip. Same thing will happen here. This, you will find values anywhere from 0.3 volts to 0.6 volts as people take. In this course, we will just assume that it is 0.65 volts. This is just a number. It is a property of the device. There is nothing you can do about it. Are we done with the device, or is there something we need, other information we need? What do we need? we need to know the relationship between IC and VBE. It turns out that IC is given by IS some exponential VBE by VT minus 1. IS is called the saturation current of the transistor. VT is not to be confused with the threshold voltage of the MOS transistor. It is the thermal voltage KT by Q, and this is approximately 26 millivolts at room temperature. A very oftenly used approximation is 25 millivolts. Exponential is of course e to the power of VBE by VT. Alright, and again this is often simplified to IC is approximately IS exponential VBE by VT. Even if VBE is, let's say, 3 or 4 VTs, that's 100 millivolts or so, you can see that e to the power 4 is about 50 or 60 or something like that. That's much larger than 1. You can neglect the 1 in relation to the exponential VBE by VT. So, a very commonly used expression for the collector current is that in the active region, the collector current is given by IS exponential VBE by VT. This is provided, it's operating in the active region, which means what? The active region is defined as VCE is greater than VCE SAT, which is about 0.65 volts. It turns out, unfortunately, that unlike in the MOS transistor where the gate current was 0, there is a base current IB, which is IC by some number beta. Ideally, this beta is supposed to be very, very large number, so in principle the input current also is supposed to be very, very small. But in practice, beta will be 100, 150, 200, sometimes 20, sometimes 10. The base current, which is a new phenomenon now, is the collector current divided by some number beta. So this beta is called the current gain of the transistor. Say for commercial transistors, let's say is typically can be 50 to, I don't know, 200. The beta can be 1000. So this beta is a small current. For the purpose of this course, we will treat it as IB flowing into the base of the transistor and of the form IC by beta. If IC is IS times exponential VBE by VT, what is VBE? VT ln IC by IS. When you have a logarithmic relationship, what does this mean? We have seen this in diodes. I mean, the exponential is telling you that a small change in VBE will cause a dramatic change in IC, turning that upside down. Large change in IC can happen with only a small change in VBE. Exactly the same thing even with respect to a diode, because the characteristic is very similar. And what did we say? If you plot the VBE of the transistor on the y-axis and IC on the x-axis, you will see something like this. It's a log curve, right? The logarithm does this, which means that over a large range in current, we see that the change in the base emitter voltage is very small. In other words, over a large range of operating currents, you find that the VBE change is very small. Then what can you say? You can approximate the VBE I mean, if somebody asks you to guess what the VBE is for this current, you would be quite accurate in estimating the VBE by, some number like this. And this value is often called VBE nominal. And the reason this makes sense is that the bipolar transistor current rises so quickly with applied VBE that estimate what VBE you would have for a given current is very straightforward. IC rises very rapidly with VBE. Large ranges of current can result only with a small change in VBE. So if somebody asks you for a first guess of what the VBE would be, you wouldn't be too far away from the mark if you just said VBE nominal was the value. And this is exactly similar to what we saw with respect to a diode in the very first couple of classes. And what is VBE nominal? Yeah, so just like in the case of the diode, VBE nominal is approximately 0.65 volts. For a given ID, if you have to find VGS in a MOS transistor, what do you have to do? Write the equations VTN plus square root of 2I divided by mu and C of blah blah blah. Blindly close your eyes and say it's 0.65 volts. Okay. This is again another common approximation used in bipolar circuits. Now that we know the equations, the next job is to find the incremental equivalent circuit. And how would you do that? We already know that IC is IS exponential VBE by VT, and IB is IC by beta. This is small signal equivalent. You treat this as a two-port. Y11 is dou IB by dou VBE. IB is IC by beta. This is nothing but dou by dou VBE of IC by beta, and IC happens to be IS exponential VBE by VT. So what is this? It is IC by beta, which is IB by VT. Does that make sense? What is Y12? Y12 is dou IB by dou VCE, which is 0. IB is a fraction of IC. IC doesn't depend on VCE because it's flat in the active region. So please note that I am finding the incremental equivalent circuit for the active region, where the collector current is independent of the collector emitter voltage. What is Y21? Is dou IC by dou VBE, and this is nothing but is simply IC by VT. I like this expression much better than 2I by VGS minus VT, or the square root of all this other stuff. And what is VT? 25 millivolts. So if you have 1 milliampere flowing in the collector current flowing in the transistor, 40 millisiemens of transconductance is what you get. This is independent of IS. In the MOS transistor, the transconductance is dependent on the geometry, W by L and mu and C ox and all that. The beautiful thing about the bipolar transistor is that regardless of IS, the transconductance of the transistor is IC by VT. And what is Y22? The Y22 is dou IC by dou VCE, which is 0. The equivalent model for the transistor is now, there is an input resistor now. It's not an open circuit like what you had for the MOS case. And the value of the resistance is beta times VT by IC. So this is B, this is the emitter, and this is the collector. What is the strength of this control source? I21 times incremental VBE. And what is this? It's IC by VT times the incremental VBE. And this IC by VT is, as usual, denoted by GM. So this becomes GM VBE. Incremental current IB. This is the incremental current IC. What would be the incremental current in the emitter? IC plus IB and which is basically IB, and IC is beta times IB, so this is simply beta plus 1 times IB. So this is the incremental equivalent of the bipolar transistor, of the so-called NPN bipolar transistor. In practice, just like we saw in the MOS transistor case, the characteristics in saturation for an ideal transistor we saw were parallel to the x-axis. So this is IC versus VBE, and in practice it turns out that the characteristics will have a finite slope. We model the slope by a hack, it's exponential VBE by VT times 1 plus something similar to lambda VC. So what in the bipolar literature you don't call it lambda, but you call it 1 over VA. VA is called the early voltage. What happens to Y22? Y22 dou IC by dou VCE, which is approximately IC by VA. For a practical bipolar transistor becomes the following, very similar to what we had for a MOS transistor. An output impedance, which is it's a voltage controlled current source, where the output impedance is not infinite. You have some GM, and in contrast to the MOSFET where the gate source incrementally was an open circuit, the base emitter is got a resistance equal to VT by IC times beta. Fundamentally, the collector current is the effect and the base emitter voltage is the cause. And just like in a MOS transistor where the drain current is the effect and the gate source voltage is the cause, here the collector current is the effect and the base emitter voltage is the cause. And just like in a MOSFET where we saw that why the characteristics must be the way they are, the same thing follows for a bipolar transistor. The DC potential between the collector and emitter must be some minimum voltage to get into this region where the characteristics become flat. This is exactly analogous to a MOSFET, so which means that the circuits will all be virtually the same. So first thing we did once we had the device was to make a common source amplifier in the MOS case. Now you make a common emitter amplifier, and the basic idea should be the same. In MOS transistor circuits, we use VDD because the topmost terminal in NMOS transistors is the drain. In bipolar circuits, it's the collector, so we call it VCC. So again, you have RA, RB, RL. Now you have actually a serious problem with this bias arrangement, and this should never be used. Why? What do you think will happen if there is a small change in RA or RB? VBE will change by a small amount. However, the transistor is so sensitive to VBE that the IC can change by a dramatically large amount. Whereas in the MOS transistor we have somehow saved because it's a square law, it's kind of gentle and so on. In a bipolar transistor it's exponential. So you should never bias a BJT this way. This is a common textbook problem. You call this RL, you call this VCC, you call this also VCC, you call this RB, and the beta of the transistor is given, and you're asked to find the VCE and the collector current of the transistor. Only an imbecile would do this. And you know the beta of the transistor. So let's assume some collector current IC. So this current should be IC by beta. So VBE will be VCC minus IC by beta times RB. Okay, this divided by VT. This e to the power of this times Is should give IC. So you go solve the equation. Okay, that's what you do. I mean, this is obviously too complicated. So a hack could be to assume that the VB of the device is, if it's conducting current, it must be approximately 0.65 volts. So another hack that's commonly used is to say the current in the base is VCC minus 0.65 volts divided by RB. That's the base current. That times beta should be the collector current. Okay, these are all ways of solving the problem. But no fellow in the right mind would ever bias a transistor this way, because the transistor is just so damn sensitive to VBE. And you must also realize that the beta of the transistor is a poorly controlled quantity. I mean, this is a valid way of working the problem, but the beta of the transistor is a very, very poorly controlled quantity. Same transistor can have a beta of 50 today, and then if you heat it up a little bit, the beta can go to 100. So any circuit that depends on the fact that the beta of the transistor is 101.23 is likely to not work at all. So you must now resort to all the usual negative feedback techniques that we use to bias the bipolar transistor. I'll quickly run through them. The first one is to use the current mirror. Again, this is a commonly used IC bias technique. If these two transistors are identical, there is a small, second order effect that we now have to be aware of. What is this current? It is 2 IB. Okay, this is IB. Alright, and this is IB. This must be 2 IB. And which means that what must be this current? I1 minus 2 IB. Alright. And what is the ratio between IB and, so this will be IB only if this is assumed to be greater than VCE sat. So looking at this transistor, the ratio of the collector current to the base current must be, is beta. So I1 minus 2 IB divided by IB is equal to beta, which means that the collector current of the transistor is, this basically means I1 is equal to beta plus 2 times IB, which means what is the collector current of the transistor? Beta IB, and IB is nothing but I1 by beta plus 2 is IC1. Some base current has to flow, so the amount of collector current left is, what is left after the base current is gone. The collector current in this transistor is not entirely I1, it is I1 minus some small amount, and clearly as beta tends to infinity, you see that the collector current tends to I1. So what do you think is the collector current here? Yeah, it is beta IB, which is what? These two transistors, this guy and this guy, have the same VBE, which means they will have the same IC. The IC1, so IC2, the collector current of the first transistor is IC1. So IC2 must be the same as IC1, which must be equal to beta by beta plus 2 times I1, which tends to I1 as beta tends to infinity. Does that make sense? If you assume that beta is very, very large, you can make an amplifier out of this chap by following the usual same old trick. If these two transistors are identical, so you choose RB. So let's assume that beta is infinity. This is VCC, this is VCC, this is RL, this is I, 1, let's say. And how do you hook on the input? Put an infinite capacitor, and then you have Vs. So can somebody quickly tell me what the quiescent voltage of the collector is? VCC minus I1 RL. What is small signal gain? Replace everything by the incremental equivalent. So what is the incremental equivalent circuit of this chap here? Open circuit. What is the equivalent of VCC? Short to ground, okay. What about the infinite capacitor? Short circuit. What about the bipolar transistor? You replace it with its incremental equivalent circuit, which is beta is infinity. If beta is infinity, what happens? This becomes an open circuit. So this is beta times Vt by Ic. Okay, this becomes open, and this is Gm times, let me call this Vx. Similarly, I replace this transistor by its incremental equivalent circuit, which becomes Gm times Vs, and there is again it's beta times Vt by Ic. And if beta tends to infinity, all these guys go away, and you are left with the same old, same old. What is the incremental gain? Minus Gm RL. You understand? The total voltage at this point will be the quiescent voltage. This will be approximately 0.65 volts plus Vs. This will be, the absolute voltage here will be the quiescent value plus the incremental value, which is minus Gm RL times Vs. The next thing to do is to find the swing limits. And how will you find the swing limits? The limit for BJT getting into the saturation region and what is that? VCE becoming equal to 0.65 volts, which means VCC minus I1 RL minus GM RL times VA sin omega t, which is the input, must be equal to 0.65 volts, which means that VA is VCC minus I1 RL minus 0.65 divided by GM RL. What is the next thing? Limit for the transistor getting cut off and what would that be? IC is 0. What is the total current to the transistor? Is the quiescent current I1 plus GM Vs, and that is Va sin omega t, and which means that I1 by Gm. Now what is Gm? Gm is IC by Vt. Okay, so this cutoff limit is Vt. And please note that again here we are making the approximation that the total current is basically the sum of the incremental current plus the quiescent current even for large signal operation. Okay? And this analysis is telling you that if the VA is Vt, the collector current of the transistor will go to 0. In reality, what happens? The incremental base emitter voltage is reduced by Vt. Collector current will not go to 0. The tangent at that point, which is that Gm, okay, there is the ratio of the slopes. I mean, is the slope here, it's Gm. Okay? We are finding how much incremental voltage I must apply so that the current goes to 0. And this analysis is telling you that based on this slope, this is only 25 millivolts. This is VBE, this is IC, this is I1. But you notice that if I reduce the applied VBE by 25 millivolts, the current is not truly gone to 0. Does that make sense? Okay, so it will never go to 0 until the until the VB becomes 0. Can somebody quickly tell me what the quiescent current will be at this point? For VB quiescent it was I1. Now the voltage is reduced by 25 millivolts. It will be I1 by E. So it's about 1/3 of E is about 2.8, 2.7. So it's about 1/3 I1. The current is not gone to 0, but it is reduced so low that the Gm of the transistor has gone down by a factor of 3. So the incremental gain is also gone down by a factor of 3. So you will see a flat top. Same stuff that we encountered in MOS circuits. You understand? So with this, I think I will call.